All right, let's jump right in. Today, we're tearing apart the mechanics of network anonymity. We're not just philosophizing about privacy here, we're getting into the actual architecture of how data moves, how it gets tracked, and exactly how we can engineer systems to obscure it. Because the reality is your data is constantly leaving a trail, and we need to understand how to control it.
So that brings us to the ultimate question. Can true online anonymity actually be achieved? Think about it. Every single connection you make, every web page you request, your machine is basically shouting its identity and location across the internet. Is it genuinely possible to beat localized surveillance and deep packet inspection on a network literally built to track connections?
Well, to tackle that, we need to understand what network anonymity actually looks like. It is definitely not a magic switch you just flip on. It's a continuous, active process of layering defenses. You're routing traffic through intermediate nodes, mathematically masking your IP address, and aggressively encrypting the transmission. Miss just one of these steps, boom, your identity leak.
Here's our roadmap for this explainer. We'll start with the illusion of anonymity, move through proxies as our first layer, VPNs as the encrypted tunnel, Tor as the onion router, and finally, actually forge an anonymity chain.
Section 1. The illusion of anonymity. Look, without deliberate intervention, you're completely exposed. Every standard TCP or UDP connection you make routes directly through your ISP, making it highly vulnerable to deep packet inspection, or DPI. It's basically like the post office not just checking the address on your envelope, but actually opening it up, reading your private letter, and taking notes. To get true privacy, we have to actively patch those vulnerabilities layer by layer.
Section 2. Proxies, the first layer.
So, let's look at the SOCKS5 protocol. Think of a proxy as an internet bouncer. You don't talk directly to a website, you talk to the bouncer, and the bouncer talks to the site for you, successfully hiding your origin IP. And since SOCKS5 operates at layer 5, the session layer, it's super versatile. It handles TCP, UDP, whatever you throw at it. But here's the massive, fatal flaw. It lacks native end-to-end payload encryption. It's like having a bouncer who hides your ID, but loudly shouts your private conversations to everyone on the street. Anyone upstream can intercept and read exactly what's being forwarded.
Section 3. VPNs, the encrypted tunnel.
Now, to fix that massive encryption gap, we bring in virtual private networks. Modern VPN protocols like WireGuard use some seriously intense cryptography, specifically the CHA-2O Poly 11305 architecture. A VPN encapsulates your entire operating system's network traffic inside an armored encrypted tunnel. It takes your message, runs it through complex math to generate a key stream, and tightly authenticates the data. It gives you absolute mathematical certainty that your local ISP cannot read or mess with your packets. But wait, there's a catch. While VPNs give us robust point-to-point encryption and perfect forward secrecy, they introduce a huge structural weakness: centralized architecture. When you use a VPN, you're basically just shifting your trust from your ISP to a private company. It's a single point of failure. If that VPN provider keeps logs, maybe they bought a bunch of flashy ads but don't actually care about your privacy, or if they're forced by a government to monitor traffic, your anonymity is completely compromised.
Section 4. Tor, the onion router.
This brings us to Tor, which provides the ultimate theoretical fix to that centralization problem. Tor multiplexes your streams through a decentralized labyrinth of 3 volunteer nodes. Your traffic gets wrapped in 3 layers of asymmetric encryption, literally like an onion. The entry node sees your real IP but can't read the payload. The middle node only knows the hop right before it and right after it. And the exit node peels off the final encryption layer and hands the traffic to the destination. Because of this brilliant design, no single node ever holds both your identity and your destination.
So comparing these technologies, our evolutionary journey becomes crystal clear. SOCKS5 proxies give us routing, but completely fail on native encryption and decentralization. VPNs encrypt everything beautifully at the OS level, but fail the decentralization test. Tor is the only technology here, sitting up at the application layer, that successfully delivers both true end-to-end encryption and the decentralized architecture.
Section 5. Forging the anonymity chain. Okay, time to step into the lab. But before we build our chain, we have to talk about the absolute silent killer of anonymity: DNS leaks. You could have the most beautifully constructed proxy chain in the world, but if your apps are secretly bypassing the proxy to resolve host names through your local ISP, your entire browsing history is exposed. We absolutely have to force DNS queries through the tunnel. Enter ProxyChains-NG. It solves this DNS leak problem using a really clever technique called hooking. Basically, it acts like a wiretap for network functions. When an app asks for a website's IP, ProxyChains intercepts it. It doesn't actually resolve the DNS right then. Instead, it feeds your app a fake IP address in a reserved subnet. The app happily tries to connect to that fake IP, ProxyChains intercepts the connection, and then securely sends the actual hostname through Tor. Tor then safely handles the real request way out on the exit node. It's a remarkably elegant trick.
Let's put this all together in 4 quick steps. First, grab a Debian or Kali Linux machine and install Tor and ProxyChains 4. Second, start the Tor service, which automatically spins up a local SOCKS5 listener on port 9050. Third, dive into the ProxyChains config file. Uncomment dynamic chain so traffic gracefully skips dead proxies, and definitely make sure proxy_DNS is enabled. Finally, you just run your tools by typing ProxyChains 4 before the command. Boom! The power of this entire architecture is right at your fingertips.
But heads up, here is a massive trap you need to watch out for. When you're running security tools like Nmap through ProxyChains, you absolutely must use a connect scan. That's the -ST flag. Why? Because Nmap defaults to a SYN stealth scan, which creates raw packets at the kernel level. That completely bypasses the user-level hooks that ProxyChains relies on. Forget that one flag, and your traffic will literally leak right past the proxy and hand your real IP straight to the target. No joke.
By layering the session control of SOCKS5, the intense encryption of VPNs, and the decentralized routing of Tor, we build an incredibly resilient architecture. But I want to leave you with this provocative thought. As artificial intelligence advances, analyzing packet timing and flow across continents in literal milliseconds, how long will our decentralized labyrinths actually remain unbreakable? The cat and mouse game never stops. Set up a lab, test these chains for yourself, and keep digging. Thanks for joining me on this explainer.